sequence is a list of numbers in a special order, and the equation of a sequence gives you the nth term in that sequence. And in this example right here, an equals 2 to the n. If you plug in 1, you'll get the first term of the sequence, which is 2. 2, you plug in 2 for n and you get 4. If you plug in 3, you get 8, and so forth. And the limit of a sequence tells you if the sequence converges or diverges. If it converges, it tells you that all the values of the sequence will eventually close in on one number. And if it diverges, that means that it will never close in on a number and it will keep increasing or decreasing. Relative rates of growth are just a general way of showing how fast one type of sequence grows in comparison to the others. So the easiest way to remember this is n to the n FEPL, just showing that n to the n equations grow faster than factorial equations, which grow faster than exponential equations, and so on. We included this on the cram sheet for easy.
What is a series? A series is the sum of the terms of an infinite sequence. You'll see these with the sigma and infinity on the top, with n equal to a number on the bottom. Then you'll have a function beside it. Convergence is when the limit is approaching a number, and divergence is when a limit is not approaching a number, it's approaching infinity. The first test is called the nth term test. This is when the limit as n approaches infinity is not equal to 0. The only way the nth term works is to determine divergence. For an example, 2n plus 1 over 3n plus 4. The limit of that is 2/3, which is not equal to 0. Therefore, the series diverges. The next test is the geometric test. This is when you have something like r raised to the nth power in your equation. If the absolute value of r is between 0 and 1, the series will converge. If the absolute value of r is greater than or equal to 1, the series will diverge. You may be asked to find the sum of the series. To do this, the sum is equal to the first term over 1 minus r. You are only able to find this if the series converges. In the example, you have n times 3/4 to the n power. r is equal to 3/4. The absolute value of 3/4 is in between 0 and 1, meaning the series converges. To find the sum, you take a sub 1, which is 3/4, over 1 minus 3/4. When you multiply those together, you will get 3. The sum of the series is 3. Our next test is the telescoping test. This test can only be used with fractions and will always converge. To start, you will separate the fraction using partial fractions like we did with integrals. Once you do this, you will then solve for a and b and plug back into your equation. Now you will begin plugging numbers in for n. You will notice that numbers will start to cancel out, and once they do, you will add the numbers together to find where the series converges. Our next test is the p-series. This is fairly easy to recognize because it has to be a fraction with n on the bottom raised to a power. If p is greater than 1, it converges. If p is in between 0 and 1, it diverges. An example of this is 1 over the 5th root of n, which is equivalent to 1 over n to the 1/5. This diverges because p is 1/5, and 1/5 is in between 0 and 1.
The alternating series test is used to check for convergence or divergence of a series that alternates. And a series that alternates usually has a -1 to the n, or a cosine pi times n, or a sine of pi over 2n in the series. That just is a signal that it's alternating. And the series will converge if the limit as n approaches infinity of the sequence equals 0, and you can use your skills from the nth term test to determine that. And also if the next term in this series is less than or equal to the previous term in the series. In this example, we have the series -1 to the n times n plus 1 over n squared minus 3. And first we're going to check if the sequence approaches 0, and in this case it does. And then also we have to check if the series, if the second term in the or the next term in the series is less than or equal to the previous term. And there's two ways to do that. You can either plug in n plus 1 every time you see an n in the original series, or you can just plug in values and then just compare the next one to the previous one and see if it's less than. And in this case, it is. So both the sequence approaches 0 and the next term is less than or equal to the previous term. So there it converges. So when you have an alternating series, you're going to want to check if the series is absolute or conditional convergence, if it does converge. So if the series only converges when it alternates, then it is conditionally convergent. And if it is convergent when it's alternating and when the normal part of it, when it doesn't alternate, then it's absolutely convergent. And you see in this example that we take away the alternating part, and it does converge, and we use the alternating part, and it converges as well, so therefore it is absolutely convergent. And for the ratio test, you're going to want to look for a series that has an exponent and a factorial, and you're going to set up a ratio, and you're going to want to find the limit of that ratio. And there's different rules. If the limit of that ratio is less than 1, then it converges. If the limit is greater than 1, and make sure that includes infinity, then the series diverges. But if the limit is equal to 1, then the test is inconclusive, and you're going to have to use another test.
For alternating series error, you are going to plug in 1, 2, 3, and 4, etc. into n of your equation until you reach or pass the error asked for in the question. For example, this question asked us to find an error less than 100. So I plugged in n equals 1, 2, 3, 4, 5, 6, and 7. When I plugged in 7, I got 1 over 128, which is less than 1 over 100. 1 over 128 is my first neglected term.
Now for the root test, you're going to want to look for a series that have an n in the exponent. And what you're going to want to do is you're going to want to just take the nth root of that of the term, and you're going to find the limit of that. And the conditions are the same as the ratio test. So if the limit is less than 1, then it converges. If the limit is greater than 1, including infinity, then it diverges. If the limit is equal to 1, then the test is inconclusive. We're going to have to use a different test. And for this example, we're going to use the series of n plus 1 over 2n plus 1 to the nth power. So we're going to take the nth root of that. And we're going to take the limit of the nth root of that is going to be 1/2, because you have a rational function and their equal exponent, and 1 over 2 is 1/2. 1/2 is less than 1, so therefore the series converges.
Now we're using the integral test. This is when you'll use an integral to find if this series converges or diverges. If f of x is positive, continuous, and decreasing for x is greater than 1, and a sub n is equal to f of n, then the series and the integral either both converge or diverge. The bounds of your integral are determined by what n is equal to on the bottom of the sigma and infinity, or what is on the top of the sigma. Then you will change all of the n's in your equation to x's. When you set up your integral, you will see it's improper, so you will have to substitute n in a letter for infinity. Once you solve the integral, you will then use it to determine if it converges or diverges. After solving the integral, I was able to determine that the limit diverged. This helps because the integral test states that if the integral diverges, then the series must also diverge.
So for the limit comparison test, you're going to want to look for a crazy looking series, and what you're going to do is you're going to create your own comparison series, and then the original series you're going to set up a ratio between the two, and you're going to find the limit of that ratio, and that's going to give you L. And where L is finite and positive, both AN, which is the original series, and BN, the comparison series, must converge or diverge. So here's an example of the limit comparison test. So we have our original function, which is a sub n, which is 1 over 3n squared minus 4n plus 5, and then we're using the comparison of 1 over n squared. And we know that 1 over n squared converges by the p-series test because p equals 2, which is greater than 1, which means it converges. And then we set up the limit, or then the ratio, and we're taking the limit of that ratio, and we get 1/3. And since 1/3 is greater than 0, and 1/3 is not equal to infinity, then both a sub n and b sub n must converge. Therefore, making a sub n, which is the original series, converge as well. So here we have the direct comparison test, and you're going to want to look for series that closely resemble p-series or geometric. And so for this, the a sub n is the given series, and the b sub n is the comparison series that you're going to make up. And so you only use this really when you have none of the other tests work. So we're going to see as a b sub n is always greater than or equal to a sub n, and the series of b sub n converges then a sub n also converges. Because we got to look at, you got to see these lines. So if b sub n converges and b sub n is always greater than a sub n, then it's going to keep a sub n under it, and they're both going to converge. And then if b sub n is less than or equal to a sub n, and the series for b sub n diverges, then the series for a sub n diverges for the same reason. Because if b sub n diverges and it's going like up, a sub n can never touch b sub n, so it has to keep diverging as well.
Taylor approximations. The nth term Taylor polynomial then has derivatives of x equals c, and the polynomial seen on your reference sheet occurs. Maclaurin polynomial is a Taylor polynomial where the c equals 0 and c is the center. Seen in this example of natural log of x, c is 1. So we first find f of 1, which is 0. Then we take the derivative of f of x, f prime of x, and plug in 1 into that. So we get f prime of 1, which is 1. And so on until we get f prime of 3. So we plug all those values into the p of x equation. So we get 0 plus 1 over 1 factorial x minus 1, because c is the center, and c is the center, plus what we get for f prime of 2, which is negative 1 over 2 factorial x minus 1 squared, plus what we get for f prime of 3 of 1, which is 2 over 3 factorial x minus 1 cubed. Then we want to find the approximation of x equals 1.2, so we plug that in for x. So p of 1.2 equals 0.2 plus negative 1 over 2, because that's 2 factorial, times 0.2 squared, plus 1 over 3, because that's 1 over 3, because that's 2 over 3 factorial, times 0.2 cubed. We get p of 1.2 is 137 over 750, or 1.183. If you look on your cram sheet, you see the elementary functions, all the ones that you need to know.
This is an example of elementary function, and so for this particular one, it's e to the 2x. And so using the first four terms of the elementary function, you plug in 2x for every time this is an x. And then going through that, you can find the nth term. And then you have to check your endpoints for finding the range. And both of them diverge, so you don't have to include equals to, it's just less than x and greater than x. Okay, so this is the Granger approximation. And it's pretty straightforward. You just have to plug in the value for n. And so for this example, it's the function of x is equal to e to the x. And you're to approximate when e is to the 1/2 power and use the first four terms. So you plug in 4 for n, and then you you find the maximum, and the center is 0. And then you just pretty much solve for it. And for z, it's a value between c and x. And then you get your error approximation.